Good day, everyone. Today I will present our work evaluating prompt-based question answering for object prediction in the Open Research Knowledge Graph. I'm Jennifer D'Souza. I work as a postdoctoral researcher in the Open Research Knowledge Graph team. This work is done together with my colleagues Musab Hu and Zoran Auer. So let's get started. At the outset, I would like to present the Open Research Knowledge Graph project under the umbrella of which this work was done. The motivation of the project, starting with the motivation of the project. Currently, scholarly articles are published at an alarming rate of 2.5 million articles per year. The limitation in this case is that traditional search methods as a ranked list of documents can no longer support efficient R&D. So here is an example of a search for the keyword COVID-19 pandemic. It returns about 2 million results. The scientists cannot be expected to go over each of these 2 million papers. Therefore, since scholarly knowledge is being produced at an alarming rate, correspondingly, the scholarly knowledge storage and access information technologies need to be rethought and re-engineered to continue to assist the science and industry stakeholders. Here we can see the trajectory of scholarly communication from over 300 years ago to today. As we can see, it remains discourse-based, so not much has changed. In other words, science does not harvest the full potential of digitalization. The scientist is still expected to scour through information buried in discourse text over large volumes of publications. Here comes the ORKG solution. It is to represent scholarly contributions in a structured manner as a knowledge graph. At the ORKG, we ask ourselves, what if the global scientific knowledge base would be more than a document repository? In this case, scientific information and knowledge would be fair also for machines. So our overarching R&D question is to help users efficiently discover new knowledge about scholarly innovations in a large mass of literature. To this end, the ORKG aims to build a digital library for machine actionable knowledge communicated in scholarly literature as a science-wide knowledge graph. And specifically, its knowledge capture target is scholarly innovations or contributions. With structured scholarly contributions in a knowledge graph, they can be automatically surveyed, visualized, and benchmarked. Thus, with machine-computable fine-grained scholarly knowledge in the ORKG, the scientist's information access needs via smart information technology is met. So now we come to our work. This work aimed to build an application for the ORKG, an NLP application of the ORKG. Let's start with the task definition of our work. The task definition reads as follows: given an ORKG predicate formulated as a question, using an unsupervised template-based generation prompting function to extract the object answer from the corresponding paper abstract context. Note the ORKG is essentially a large-scale knowledge graph whose instances in RDF syntax are represented as subject, predicate, object triples. So essentially at the heart of the ORKG are collections of triples that represent a paper contribution. And the same model is then used for all the papers whose contributions are recorded in the ORKG. Here we see an example. This is a paper and its contribution with its structured statements. The first level of the graph looks like contribution, predicate, object. And one paper's contribution has multiple statements to describe it in a wholesome manner. So going back to the definition, given an ORKG predicate, that's fed into a prompt function and then converted into a question. So here is an example. A predicate as approach name is then fed into a prompt function. A prompt function is nothing but an unsupervised question generation method. Basically, it prepends WH question words to the given predicate and then ends it with a question mark. So here are the 4 variants of question types generated by our unsupervised method. This method is inspired from Fabry et al., who produced the work template-based question generation from retrieved sentences for improved unsupervised question answering. So that's the first part of the task. Given a predicate, we convert it into a question in order to extract the object answer from the corresponding paper abstract. So given the task definition in place, the plan for the rest of the talk is to introduce our dataset, approach, evaluation, and results. So let's start with the dataset. On this slide, you see some example instances from our dataset. Each instance comprises a question, which was originally a predicate in the ORKG, an answer, which was originally an object in the ORKG, and a context from which the answer must be extracted. Thus, our task alternatively can be called extractive QA for the scientific domain. We only use paper abstracts as the context. And based on the 4 question types generated, there are 4 experimental dataset variants created for each question type, respectively. Note an important characteristic of our scholarly domain corpus is that it is multidisciplinary. Let's take a look at the examples in the table. The first table speaks about an approach, so it could belong to the computer science domain. The second abstract speaks about biotic resistance to a lineage of a model invasive species in North America, so this could belong to the agricultural domain. The third abstract speaks about solid lipid nanoparticles for colloidal drug delivery, so this could belong to the biomedical domain. This resulting corpus we call as the prompt ORKG corpus and is publicly released. The link can also be found in our paper. As an aside, our data is structurally similar to an existing well-known dataset in the community, namely the Stanford Question Answering Dataset, or SQUAD for short. Basically, the SQUAD dataset also has a WH type question. It has an answer, which is an extractive objective from a context. So the only distinguishing factor is the domain. SQUAD handles general knowledge from Wikipedia, while we handle scholarly knowledge from scientific papers. Our choice of this dataset design will become clear when our approach is discussed eventually. So on this slide now, we delve into some of the details of the prompt ORKG corpus by describing the steps that we followed to create the corpus. So as a first step, we use the ORKG REST API to fetch all triples with the contribution node as the subject. Note that the number of contributions here is greater than the number of papers. So this is not a false number because a paper, and is possible because a paper can have multiple contributions. So as a second step, for all the papers, we fetch their abstracts from Semantic Scholar Crossref. Note's abstracts were found for only a subset of the total papers. And further, we only retained those predicate object tuples whose objects could be found in the abstract. Thus, our resulting proved dataset size was much smaller than the raw dataset, with a total of roughly 6,000 predicate object pairs than the original 100,000 pairs in the raw dataset. So now let's take a look at our approach. Our approach is predicated on the following hypothesis. Our machine learning test specifically sought out empirical evidence for the transferability of the probabilistic parameters of existing large-scale transformer models at the time of writing of this work. So in this respect, we were interested in 2 main strengths of the transformer models: to query over an open class of relations, and to also tap into the benefit of training models that were already trained on structurally similar data. In this way, we could then control for the task learned structural parameters and only test in a sense for the domain adaptability of this model. Thus, we then, as a natural choice, selected optimal SQUAD-based transformer model variants, since the SQUAD dataset is more structurally similar to ours. The selected language model variants are based on BERT, which similarly introduced the mass language model, Closed-based pre-training objective based on bidirectional self-attention architecture. So specifically, we chose 3 state-of-the-art models on the SQUAD dataset as reported on Hugging Face at the time. One was a BERT-based model, another was a Roberta-based fine-tuned model, and the third model was a distilled fine-tuned model on the SQUAD dataset called Minialab. Now, just quickly, we want to juxtapose the advantage of the transformer-based architecture for information extraction tasks. In the past, we followed the classical NLP, i.e. pipeline. And in this case, as humans, we were required to feature engineer modules into the system that handled the design of features that were relevant or informative to the task. But this is now all replaced with a single model. Of course, it reduces the explainability of the model itself. Nevertheless, the black box models have proved to be very effective, where the features are simply the learned parameters of the deep learning neural model and do not entail any feature engineering or special component design by humans. So with this, we complete our approach, and now we move on to the evaluation and results. For evaluation, our evaluations were considered in two main settings: strict, that is exact match, and relaxed, containment match, where the goal answer was checked to be contained in the predicted answer. In both settings, the main metric is the standard F1 score as a harmonic mean of precision and recall, and accuracy was used complementarily. So now diving deeper into our experimental settings, there were 5 dataset variants created, 4 of which I've already introduced before. There is one more dataset variant here called unchanged. This is basically the predicate used as a query as it is, without prepending or attaching to the end any question marks. Second, each model F1 score is reported for the vanilla model before the backslash, that is, this model tested out of the box, and the juxtaposed against the fine-tuned version of this model on our dataset. Accuracy scores are all presented within parentheses, and they follow the same format. And our results are reported in 2 settings: exact match and relaxed match. So now, in order to examine our results, we formulated a few research questions. A sub-question to the first main research question is, how do the BERT model performances contrast when queried out of the box as vanilla models versus after being trained or fine-tuned on our corpus variants? The results from the trained models on our corpus variants are approximately 25% and 35% higher, respectively, than when testing the untrained vanilla models on data from new domains. A second sub-question under the first main research question is it effective to adopt the squad format structural representation to optimally query the large-scale squad fine-tuned language models? So for this, we compare our unchanged dataset variants with the dataset variants that were created structurally similar to squad. And we see, examining the row average results, we see the results from the squad format dataset variants are 5% or 6% higher than the unchanged dataset. Note that the squad format dataset variants report results in the range of 21 to 22% F-score, while the unchanged dataset evaluations report only 16% F1 score. Thus, we can conclude that indeed the squad format task formulation as the 4 variants in the prompt ORKG corpus is an effective strategy to optimally stimulate the probabilistic parameters of the language models towards their transferability on a new domain, that is, scholarly domain. Our second main research question, finally, is which dataset variant produced the most optimal models? And in order to do this, we take a look at the results from the dataset variants themselves. And we find, examining the row average results in the table, we observe that results from the which variant is statistically insignificantly better than the what variant, with 22.6% F-score versus 22.2% F-score. This indicates some directions for future work to examine the automated generation of the questions by selecting and applying the most suitable question type, which or what, for the predicates. Finally, examining the column average results, we find that the Roberta squad model proved optimal for transferability on our problem. So with this, some of the takeaways of my talk are, I have introduced a scholarly knowledge extracted QA task. For this, we released the prompt ORKG corpus. We fine-tuned an optimal transformer model of the task. In order to do this, we needed to define certain criteria for optimality for our transfer learning task. Our fine-tuned models are available on Hugging Face. The potential application of a work, once it's able to achieve strong performances that are suitable for a practical application, is as an automated ORKG completion service or an object recommendation service for users of the ORKG. The code to reproduce our dataset and fine-tune the model is also publicly released. Thank you for your attention.